excuse me, I apologize, I spoke too soon. Exam is due Friday by 11:59 p.m., right? So make sure that you're getting that done. Obviously I can't wait for the exam to be done in order to teach new materials. So today I'm covering the beginning of unit 3, which goes over sets, Venn diagrams, and probability. And so again, the content that I'm covering today relates to homeworks 11 and 12. It is by no means a exhaustive coverage of those, but again, I try to hit on what I think are the most commonly missed or commonly struggled with concepts. Okay, so before I jump into that, are there any questions? Okay, well, I will share my screen and we will get going. All right, so what we are looking at here is just a little bit of information about sets and Venn diagrams. Again, there's way more information that you will see and learn and hear and all of that business in the main videos for the instruction, right? But in order to be able to talk about Venn diagrams, we do need to talk about these couple of definitions. So the union of sets, the union of two sets is the set that has all the elements that belong to one or both. The union of set A and B is written as A union B. And again, this is just our formal mathematical definition written out using our mathematical shorthand, right? So again, it's saying that it's A union B is the set of all elements X such that X is an element of A or X is an element of B, or they could be in both. So the union really is just saying A or B. It's in either, or it could be in both. When I think of unioning sets, I think of them getting larger because if you think about like a labor union is a large group of people, right? It's the summation of everyone. So again, when we're unioning sets, that stuff is going to get larger because we're just bringing them all together and creating a larger group. And then we have the union rule that says if you're trying to find the number of elements within the union of the sets, you're going to take the number, oops, I'm missing a sign here. Sorry, guys, that should be plus. So again, the number of elements in A union B is going to be the number of elements in A plus number of elements in B minus the number of elements in A intersect B. And the reason we have to take that intersect out is that when we add those two individual sets together, the intersect represents where they overlap, right? The items that are common to both. And so when you add those two individuals together, it ends up having a situation where we're double counting, because if something is in set A and it's in set B, when I add A and B together, I have counted it twice. So we have to remove the intersect in order to remove that double counting. So as I said, the intersect though is where two sets overlap, and it's the elements that belong to both sets. And it says that we have that like upside down U, the arch, however you want to say it. And again, this is saying A and B, meaning it has to be true to both of them. And when I think about intersections, think about where you're driving, right? You've got one road that intersects the other, so it's where they overlap, right? And if we think about in terms of sets, and if it's getting bigger or larger, we're looking at just the items that are common to both. And so we're going to be narrowing down what we're looking at. So again, we're getting more specific. It's going to be a smaller amount. If we look at A intersect B, again, the formal definition is the set of all elements X, such that X is an element of A and X is an element of B. sets that do not have anything in common are called disjoint sets. And if two sets are disjoint, that means that the intersection is equal to the null set. This is the null set. Don't write 0, okay? Because that would indicate that the intersection of A and B is 0, which is a value. We have to have the null set. Another way we can write this is A intersect B can equal the empty set, which is the set with nothing in it. That's another way to write it. But don't ever put the null set symbol inside set brackets. You either write the null set symbol by itself, or you write the brackets on their own, okay? Oh, really quick, just to talk about, when we think about Venn diagrams, with the union of sets, if I were to draw a little mini Venn diagram here, and I have sets A and B, I have to tell students that when you're unioning two sets together, in a Venn diagram sense, think of just continuing to color all with the same color. And so if I were to color A and B, or excuse me, A and blue, and I wanted to union it with B, I'm just going to keep going and color B that same color. So again, that Venn diagram there represents A union B. Well, the intersection is where we would think about two colors overlapping. So I know these are really small. So if I have A and B, let's say I color A in yellow and I color B in blue. Well, the intersection is where yellow and blue overlap, which you can see there looks green. So the intersection is that green space. A intersect B is just where they overlap together. So if I just wanted to color that, it would be this color right here, this shaded spot right there. That would be A intersect B. The idea of disjoint sets are two sets that have nothing in common, meaning they do not overlap. So we would draw two standalone circles, A and B not overlapping. And then finally, the complement of the set. The complement of a set is the set of all elements in the universal set, U, that are not in the set. So if I have this rectangle, and this is going to represent U, the universal set, and I have set A, well, then everything that's outside of that circle is the complement of A. And you'll see A complement written as A with sort of like an apostrophe, or you'll also see it as A with a little tiny C above as the superscript. So those are two ways that they might write complement. So your homework does have you go through sets and things like that, but I want to focus on solving Venn diagrams. And so this first problem that I have here is a Venn diagram that requires 3 circles because we have 3 sets that are intersecting. When drawing a Venn diagram, it's always important that you have not only the circles, but also the outside rectangle or square that represents your universal set that everything is applied to. So I'm going to draw a picture. Okay. And so I've got 3 circles. And we're going to have to name these circles something, right? So we're doing a genetics experiment on 51 pea plants. The number of plants having certain characteristics was tallied with the following results. 19 were tall, 25 were green, 34 were smooth, 8 were tall and green, 18 were green and smooth, 4 had all 3 characteristics, and 7 had none. And then it says answer the following. Before we can even get into answering the following, we have to draw a Venn diagram that fully represents what's happening here, okay? You have to solve all the spaces before you can start answering the questions. Now, like I said, you want to make sure that you have that rectangle that represents the universal set. And in this case, the universal set is all the possible plants that they looked at. And in the instructions, it's telling us that they looked at 51 pea plants. So I'm going to remind myself that this whole thing has to equal 51. And when I say the whole thing, I mean, if I add up all the regions of the Venn diagrams, plus that space outside, all of that has to equal 51. Now, when we break down our plants, we can have tall plants, we can have green plants, and we can have smooth plants. So when you go through the list of information, there's always two really good places to start. One of the really good places to start is the full overlap, okay? And that's going to be this space right here, okay? That middle. And that is saying where tall is intersecting green, which is intersecting smooth. And if they're intersecting, that relates to this concept that there's 4 plants that had all 3 characteristics, because in order to have all 3, it had to intersect at all those spots. So I'm going to start by putting 4 in here. Once I'm done, I just cross it out. Another place that you can what am I trying to say? That you can start with is looking outside of everything, right? And so we're looking at the plants that aren't green, aren't tall, aren't smooth, okay? And that's this region here. And we call this the union of those, but it's the complement of the union, okay? So that region out there represents the area that is not tall or green or smooth. It can't be any of those things. So they're short, yellow, bumpy peas, right? For lack of a better way to describe it. And since it tells us that 7 had none of those characteristics, we can put those 7 out there. So from there, we can start moving in and looking at other pieces. Now, when you look at the first 3 values they gave us, 19 are tall, 25 are green, 34 are smooth. Those are too broad because those represent those complete circles for each of those regions. But there's not enough information yet to use those. So then we go to the next piece of information, and it tells us that we had 8 that were tall and green. It doesn't say that they were 8 that were tall and green only. It just says 8 were tall and green. So if we look at where tall and green overlap, we've got 2 spaces here, right? We've got the complete intersect plus those ones that are tall and green, but not smooth. So this 8 being tall and green represents the sum of both of those spaces because it's where circle tall overlaps with circle green. Now, again, if they had said 8 were only tall and green, that would represent that smaller space above the 4 because that's excluding the smalls, okay? Or excuse me, excluding the smooths. So because it doesn't say there's the only piece, it just says 8 were tall and green. That tells us that the sum between those 2 spaces has to be 8. So in order to solve for the space that we were looking for, we're going to do 8 minus 4, which gives us 4. So we've got 4 in there that were tall and green only. Okay, so we've used that. We can cross it off. Now I've got 18 were green and smooth. Okay, so looking at green and smooth, just like with tall and green, green and smooth represents 2 regions. Okay, and so with those 2 regions, we need to again subtract just like we did before. So I'm going to go 14 minus the 4 that I've already used. Oh, excuse me, not 14, 18. I'm jumping ahead. I'm looking at my key here. 18 minus the 4, because again, we had 18 that were green and smooth right there. And we're taking the 4 out that we've already accounted for. And that's giving us that 14 here. So now we can see by looking at this, we almost have that circle of green completely accounted for. And once we see that we've got 3 of the 4 spaces, and when I'm talking about 3 of the 4 spaces, again, that circle green has the 4 that are tall and green only, the 4 that are tall, green, and smooth, and then the 14 that were green and smooth only, right? then there's just the ones that were green that aren't part of that. And so from here, what we want to do is we're going to use this piece of information here. The fact that it tells us that we had 25 green. So to get this last space, we're going to do 25 minus the pieces we've already used. So we've got the 2 4s plus the 14. All right, so simplifying that, 25 minus, and what is inside is 22, gives us 3. And so we've got 3 in that space right there. So I'm going to pause there. Any questions so far? Okay. So now we're looking at this and going, okay, well, we've used the none, we've used the all 3, we've used the 18, we've used the 25, and we're left with 19 tall and 34 smooth. But when we look at the spaces that haven't been filled in on our Venn diagram, we have 3 spaces to account for. And so this is where we actually have to use a variable to start building out the rest of our Venn diagram, because we don't have another piece of information that's telling us about tall and smooth overlapping at all, right? So what we're going to do is we're going to start by putting a variable x here. You want to put that variable where the overlap is happening, because that allows us to build out from there. Okay. We know that we had 19 tall. So in order to solve for this remaining tall space, we're going to take the total for tall and we're going to take out what we've already used. Well, we've already used x, we've already used a 4 in the middle, and we've already used a 4 where that tall and green only were overlapping. We want to simplify this. So 19 minus 8 is going to be 11. So we get 11 minus x. So 11 minus x is going to represent that space there. And so from here, we're going to then go down to small, or I keep saying small, smooth. So we now have 34 smooth, same idea. We're going to take that 34 and we're going to take out what we've already used. So we've already used the x in the overlap, the 4, with it, all 3 come together, and then the 14. So subtracting that out, we have 34 minus 4, which is 30. 30 minus 14 is going to be 16. So we've got 16 minus x that is in that spot. So you might be looking at this now and go, great, Erin, everything's in variables and I still don't know what we want to do. Well, there's one last piece of information that we haven't used. Again, crossing things out as we go through. At the very top, remember I told you it was really important to recognize that that whole rectangle, the whole, what am I trying to say? The universal set, all the plants that we're discussing, is represented by 51 pea plants. And so the 51, that sum of the total number of pea plants, has to equal the sum of all the individual pieces. So what that's going to look like is we're going to take our 51 and we're going to set it equal to the sum of each of the pieces. So when I say each of the pieces, in the tall only, I have 11 minus x. Then I want to add to it the 4 that are in the tall and green, okay? Then I want to add to it the 3 that were green only. I'm just going through this, through the Venn diagram in, what am I trying to say? In just like an organized fashion. There's not any sort of like, oh, well, she's choosing this one and then this one. No, I'm just trying to make sure I get all the spaces, okay? So the next space is going to be, so here, let me highlight what I've already used. The next space is going to be x. So I want to add in an x. Then I'm going to add in a 4. Then I want to add in the 14. Then I want to add in that 16 minus x. And then finally, the piece we can't forget are the ones that are outside here, right? The 7. So I'm going to add that in. All right, so I'm going to let you finish solving for x and let me know what you get. Okay, think about combining like terms on the right-hand side and then solving for x and then tell me what you get. Okay, so if we go through and add 11 and 4 make 15. 15 plus 3 is going to be 18. 18 plus 4 is 22. 22 plus 14 is 36. 36 plus 16 is 52. 52 plus 7 is 59. So we end up with 51 equals 59 minus x plus x minus x. Well, the minus x plus x business cancel each other out. So we're left with 51 equals 59 minus x. We'll subtract 59 from both sides, which gives us negative 8 equals negative x. Therefore, 8 equals x. Okay. So going back into our Venn diagram, if this has already gotten a little too cluttered for you, feel free to, we can just draw a new one, okay? We can put all of our values in it. So I've got tall, green, smooth. Again, all of it has to equal 51. We have 7 out here, 4, 3, 4, 14. Now we know that x has to equal 8, so which means we start here with our 8. Up in the tall only, we have 11 minus x. So we would do 11 minus 8, which is 3. And then down here, we've got 16 minus x. So we'll do 16 minus 8, which is 8. And so now we have our full Venn diagram filled out. Again, you have to fill the whole thing out before you can even start to look at answering the questions. Question number 1 says, how many plants how many plants were tall and had smooth peas? So tall and smooth It's not saying tall and smooth only, it's just saying tall and smooth. So tall and smooth, they intersect here at 2 spots. So because the circles tall and smooth intersect at 2 spots, that's going to be 8 plus 4, which is going to be 12. Okay. Let me copy this so we can use it on the next page. Okay. Number 2 says, how many plants were tall and had peas that were neither smooth nor green? So they have to be tall, which means we first think about our circle right here, the whole tall circle, but they can't be smooth or green, which means we have to look outside of where the circles green and smooth are, which tells us we only have 3 here that are tall only, right? Because that tall only is that region where there's nothing else that's overlapping it. And then finally, number 3 says, how many plants were not tall, but had peas that were smooth and green? So they can't be tall. So that excludes the whole circle of tall, okay? And then it says, but they were smooth and green. So smooth and green overlap at the 4 and the 14, right? But they're not allowed to be tall. So that's only this region here. Those are the only ones that are smooth and green, but not tall, okay? And so that's where we have the 14. Again, I highly suggest drawing pictures, using your pens, pencils, highlighters, whatever can help you to color these regions to help focus on what they're asking for, okay? So before I move into probability, any questions about Venn diagrams? Okay, so let's look at probability. So the probability that an event will occur, written as P of E, is the number of elements in the event divided by the number of elements in the sample space. So really we think of that as how many ways E can happen out of all the possible outcomes, okay? For any event, the probability of the event must be greater than or equal to 0, which is considered an impossible event, or less than or equal to 1, which is a certain event. A probability of 1 means that it's going to happen 100% of the time. It's impossible to have a probability greater than 1 because you're saying that something's going to happen more than 100% of the time, which is impossible. And again, as you can see, we think of probability has to be between 0 and 1. When a probability is calculated based on data gathered rather than theoretical calculations, this is called empirical or experimental probability. This is calculated by taking the number of favorable outcomes divided by the total number of trials. Just like we had the union rule that we applied to sets and Venn diagrams, we're seeing that again here with probability. So to find the probability of the union of 2 events, A and B, in a sample space S, we must find the probability that each event and then subtract out the intersection. Meaning, again, we're avoiding double counting. So we say that probability of A plus the probability of B minus the probability of A and B both occurring, okay? And just like with that complement rule, in terms of Venn diagrams, the same is true with probability. The probability of an event not occurring is 1 minus the probability of A, because it's the complement. All probabilities have to add to be 1. And so if we have an event occurring and we say, what's the event of it not occurring? That's going to be the opposite. So we're taking that away from 1. Again, this is also referred to as the probability of the complement of A. And as I said before, you can represent that with a apostrophe or a little c. Again, I like to make myself pictures. So with probability, we talk about drawing tree diagrams, which is what I'm going to do for this first example. But always try to visualize what you're talking about, or else it makes it really hard to wrap your brain around, right? And so in number one, it says a fair coin is tossed 3 times. What is the probability of exactly 2 heads showing? So what I mean by a tree diagram is we think about in our coin, on our first toss, we can get a head or a tail. Now, I recognize that if you were tossing a coin in real life and you flipped it up in the air, it could twirl about and land right on its edge, right? Insane, but it could happen in the experimental world. Right now, we're talking about theoretically what would happen. And in theory, coins are evenly sided. Their probabilities are independent of each other, meaning you have the equally likely outcome of getting a head or a tail. Each next occurrence of a head or a tail does not matter on what you got previous. Okay, so again, we're saying fair coin. That term is important because that does indicate to us that they have even probabilities, right? If it was a weighted coin, that would mean something different. But right now we're talking about fair coins, which means it's either heads or tails. Okay, so on your first toss, we can get a head or a tail. Then when we go to the second toss, we're building off of what we already got for the first toss. Okay, so on our second toss, we can get a head or a tail, and a head or a tail. The reason I wrote 2 branches is because it's dependent on what we got first, right? So if I got a head first, then on that second toss, I can get a head or a tail. And then finally, we have our third toss. And of course, these can get kind of messy as they get bigger. But again, it's that nice visual reminder of what's going on. What does this sample space actually look like? So if I move through my probability tree, my first possible outcome would be that I got 3 heads in a row. So I would write that as 3 heads in a row. After that, I could get 2 heads and a tail. That exhausts all the ways to get 2 heads in a row. Then we look at the next outcome would be getting a head, then a tail, then a head. After that, we have a head and 2 tails. And that's all the ways we can flip a head first, right? So you can see those first 4 outcomes are all of what would happen if we flipped our coin and we got a head first. After that, we move down to the next part, which says we can have a tail, then 2 heads. Then we're looking at a tail, then a head, then a tail. Then we have 2 tails and a head. And finally, our last outcome is 3 tails. Writing out the outcomes gives us an idea of what our sample space is, right? And so how many outcomes do we have? Well, the total number of outcomes we have here, we have 8 possible outcomes. Now, this is with us assuming that order matters, right? We're saying that each of these is distinct because of the order in which they occur, okay? So if it's saying, what is the probability of getting exactly 2 heads showing, meaning you flip your coin, what's the probability that your heads, we have 2 heads and only 2 heads? Well, if we look at our outcomes, we can get 2 heads, then a tail. We can get a head, tail, and then a head, or we get a tail and 2 heads. Those are the 3 ways where we can get exactly 2 heads. So we would say that the probability that our heads are equal to 2 is going to be those 3 possible outcomes out of our total 8 possible outcomes. And so again, giving us that visual reminder of what all is going on here is really helpful to make sure we don't miss anything. And again, we can see what our whole sample space looks like. Okay. You'll notice in these problems, we have you toss coins and pull cards and roll dice and all sorts of things like that. Okay. And so again, looking at what your sample space is very helpful. So in this next problem, it says the numbers 1, 2, 3, 4, 5, and 6 are all written on slips of paper, and 2 slips are drawn without replacement. What is the probability that the sum of the numbers is 9? Again, you can go through and just sort of like write these down however you want. This is a variation of rolling 2 dice, okay? But we're adding an extra piece into it, which says that the pieces of paper are drawn without replacement, meaning when you take a number out, you don't put it back in, okay? So if we were to look at our sample space, I'm going to draw a really big grid. Okay, so here are all of our numbers. Now, the reason why I've drawn it this way is that I'm going to say that this is my first slip, and then along the top here is going to be my second slip of paper, right? I reach in, I pull one number out, I put it in my pocket, and I go and I reach in again. Now, if you looked at the card sample space, or the dice sample space of rolling 2 dice, there ends up being 36 outcomes. But this one's a little bit different because of the fact that we're not allowing for replacement. So if we can't replace it, that means that if on the first slip I draw a 1, I don't put it back in. I am left with only the numbers 2 through 6 to choose from, which means the location of 1, 1, meaning 1 on the first top, or the first slip, and 1 on the second slip isn't possible, right? So we think about our ordered pairs here. We can have 1 on the first, 2 on the second, which gives us a sum of 3, okay? 1 on the first, 3 in the second, which gives us a sum of 4, 1 on the first, 4 on the second, which is a sum of 5, 1, 5, which is 6, and 1, 7, which is 8, right? Those are the sums, and then we've got our order pairs just indicating how we're pulling them, okay? Once we finish that row, we're going to go down to the bottom, or go down to the next row, excuse me. I can do a 2, then a 1, giving me a sum of 3, but I can't get 2 2s in a row. I can get a 2 and a 3, giving me a sum of 5, 2 and a 4, giving me a sum of 6, 2 and 5, sum of 7, and 2 and 8, or excuse me, 2, I'm jumping ahead on what I'm saying, 2 and 6, which is a sum of 8. Oops, I jumped ahead on this one too. Okay, so Titus, you're correct. I meant to say 1 and 6, not 1 and 7. So it's 1 and 6 for a sum of 7. So you get the idea of kind of what's going on here, right? If we think about it, the spaces that we can't have occurring are our double values, right? These are the ones that are never going to have values in them, right? So we could sit here and draw and fill out the rest of this. I don't want to waste our time doing that. Obviously, I encourage you to do it though, just because it's really helpful to visualize it. But if we're looking at the sums of 9, how do we get a sum of 9 using these? Well, with a sum of 9, I can have a 6 and a 3, right? That's going to be right here. I can have a 5 and a 4. I can have a 4 and a 5, or I can have a 3 and a 6. Okay. So when we're looking at our sums of 9, we've got 4 of them. Okay. So the probability that the sum is equal to 9 is going to be 4 out of, well, I know I didn't finish the rest of this filling it in, but if we look at, we've got 6 by 6 grid, which gives us 36 total outcomes, but we've accounted for those 6 blue boxes that I've shaded out as not being possible. Therefore, we have 30 total possible sums. I recognize that there are sums that are repeated, but we're saying that these are unique sums in the sense that we're looking at the order that we're drawing the pieces of paper, okay? So the probability that the sum is equaling to 9 is going to be 4 out of 30, which we want to reduce to 2/15. And then some of your homework problems will ask you to convert these to decimals. I'm fine with leaving it as a fraction. Okay. So that without replacement piece is really important. If they hadn't said without replacement, if they had said two slips are drawn, you would then assume that they were replacing it. Okay, because if they're not telling you that they're not replacing it, then we just assume that they are. Okay, so you do need to pay attention to that. If are they telling you about replacement or are they not telling you about replacement? Okay. So next one is again why I really harp on drawing pictures. Because when we look at number 3, this is kind of confusing because it's just like a whole bunch of symbols it's all of our mathematical shorthand, right? So number 3 says, suppose the probability of E is 0.26, the probability of F is 0.41, the probability that E intersects F is 0.16, and then it says, find all these things, okay? So before we even think about finding the stuff, let's focus on what information they gave us, okay? So we have 2 events here. Again, we're going to start by drawing a Venn diagram to represent this. So I have 2 events, E and F. Now, with probabilities, we want all of this to add to 1 because all the events in a sample space, the sum of them would have to all be 1. Okay, so I put that little -1 out there to remind myself that I've got 4 spaces, and when I add those 4 spaces up, they have to equal 1. Okay, and so what are my 4 spaces? Well, I've got space 1, space 2, space 3, and space 4. Those would be my 4 spaces. So just like we were doing with the Venn diagram before with the P's and the what and all that, I always say start where you can with the overlapping. So remember this space right here, the green space is is the probability of E intersecting F, right? That's where they are overlapping. So we want to start with that part and build out from there. So the green space is going to become 0.16 because again, they told us that piece right there. So we've used it so we can move out from there. Okay. When we think about the probability of E, the probability of E is this whole circle. So the probability of E is really our yellow space plus our green space, right? It's the sum of those 2 spaces together. Well, we know that the probability is 0.26. We don't know what the yellow space is, but we do know that the green space is 0.16. So this kind of gives you an idea of how you can work backwards and start filling these spaces in. So if we subtract 0.16 from both sides, we get 0.1 is equal to our yellow space. So we can go over to our drawing and do 0.1 right there. Again, the same idea for the probability of F. Probability of F is going to be our green space plus our blue space, right? We know that the probability of F is 0.41. We know the green is 0.16, but we don't know what that blue space is, right? So again, we're going to subtract from both sides. And we end up with 0.25 is equal to our blue space. Okay. So going up to our drawing, we can put in 0.25 here. So now we have one last space that we need to come up with, which is pink. Pink is everything that's not in those circles, right? So in order to find the pink space is actually equal to 1 minus the union of E and F. Because if I were to union those two together, I would bring those two circles together. That's all of it. And so that's going to be 1 minus 0.1 plus 0.16. Oops, I'm running out of room. Hold on 1 second. Let me write this farther over. 1 minus 0.1 plus 0.16 plus 0.25, right? It's 1 minus that stuff that we've already used, because again, all 4 of those regions, yellow plus green plus blue plus pink, if I add them all up, it has to equal 1. So if I add those up, I'm going to have 1 minus 0.51, which gives us 0.49. So now that we have filled in this Venn diagram, we can actually get to what they're asking us, okay? So the first question is, find E union F. After you've created your main Venn diagram, when you start to answer these little individual questions, again, I suggest drawing a sample Venn diagram just for coloring purposes. And what I mean by that is, again, we're looking at just trying to visualize what's going on here. And so if we're saying E union F, remember we're unioning them together, meaning we're bringing them together. It's going to create a bigger set. And so we're coloring E, and then we just keep coloring into F. And so that represents the union of those two sets. Well, if we think about it from the number standpoint, meaning what's in those regions, E union F is going to be those 3 regions together. And yes, I know that I already talked about that here, but again, we're just going to say 0.1 plus 0.16 plus 0.25, which is going to give us that 0.51. So having those small individual drawings can be really helpful in order to visualize what's happening, okay? So the second one they're asking for is the probability that E complement intersects F. Well, if we again draw a mini Venn diagram, E complement is going to be everything that is not E, okay? So if it's not E, we're looking at outside of E. Well, this is all the stuff that is outside of E, okay? So with intersections, remember, we are looking at where do they overlap. So if I'm color coding it, I'm reminding myself, okay, E complement was highlighted in this light blue. So now if I go up here and I grab the yellow, what's F? Well, F is this whole circle here. So I'm going to shade that. And I can see what is the intersection. It's where those two colors are overlapping, okay? So this piece right here is going to be E complement intersect F. And if we go back, let me zoom out. We go back to our main drawing. What is the number that's associated with that space? Well, the number that's associated with that is going to be 0.25. So the probability of E complementing intersecting F, E complement intersecting F is going to be 0.25. So I want you to think about what I did in number 2. I know that I'm running out of room here. The next one is going to be probability of E intersecting F complement. And I want you to try that one and send me your answer in direct message. Okay, so E intersecting F complement. So if I draw my Venn diagram, my little bit baby ones. So if I look at what's E, I'm gonna do E in pink. So here's my circle of E. Color that in, okay. And then I'm gonna do F complement in orange. So F complement is everything outside of F, okay. So if I go outside of F, I gotta make sure that F doesn't get touched, and then we do everything outside there, okay? So we can see that when we finish, oh, I gotta let my board catch up. When we finish coloring, I know it's a little hard to see with those, one of the colors is kind of light, but we can see where those two colors overlap, right? And that overlap happens right here on this half, oops. Let me make it a darker color. This half moon of E, right? This half moon of E is where those two values are overlapping. And so what is the number that's associated with that? Well, that space right there is 0.1. Therefore, the probability of E intersecting F complement is 0.1. All right, the last one, probability of E complement unioning with F complement. I know I'm running out of room on my page here. Because we're looking at a union, we want to look at using a single color to shade everything. So if I draw my little mini diagram, and I go up and choose a color, let's use green. So E complement is everything that's outside of E. Okay, so I'm coloring that. And then F complement is everything that's outside of F. So if I draw my circle around F and I color outside that, we can see that what gets colored is everything that's not the intersection. Okay, so what that tells us is that E complement union F complement, because the only piece that's not covered is that intersection, that means that it's equal to 1 minus the probability of E intersect F, which is an identity, okay? We don't really harp on these identities a lot because I don't really expect you to memorize them. I want you to be able to derive them by like doing what I'm doing right now, which is coloring. But that is a identity. And so we can say, because we can see that, we're gonna go, okay, well, that's 1 minus that intersection, which is 0.16. Which gives us 0.84. So again, coloring those regions is going to give you the best visual idea, okay, of what's going on. And again, my instructions to you are always start by doing your first Venn diagram and filling in all those values, right? That first one, and then from there you can build off to figure out the smaller pieces. I know we're like right almost at our time. I keep doing this. I always want to teach too much. I apologize. I just really quickly want to talk about probability distributions because this does come up on your homework. And I talked briefly about the fact that all the probability outcomes must add to 1. So this is looking at it from what we refer to as a distribution. So if we have a sample space and it consists of n distinct outcomes, we have the outcomes are going to be S1, S2, up to Sn. An acceptable probability assignment consists of assigning each outcome, Si, a number Pi, which is just the probability, according to these rules. Each of the outcomes has to be a number between 0 and 1. So no negative probabilities. The sum of all possible probabilities, the sum of all possible outcomes is 1. So if we look at these tables here, we have table A, B, and C. I want you to tell me which of those you think are valid distributions. Again, you can't have all the probabilities have to be between 0 and 1. The sum of all the probabilities has to equal 1. And anything outside of that makes it so it's not valid. So in our first probability distribution, we can tell right away it's not valid because one of our individual probabilities is -1, right? So the outcome S1 has a probability of -1, which makes it not valid. Looking at distribution B, all of our probabilities are between 0 and 1. If we add them all up, 0.1 plus 0.2 is going to be 0.3. 0.3 plus 0.3 is 0.6. 0.6 plus 0.4 is going to be 1. And so again, this sum equals 1. Therefore, it is valid. It's not just that it equals 1, and all probabilities are between 0 and 1, right? Last one, if I look at those, all those probabilities are between 0 and 1, but if I add them up, 0.3 plus 0.2 is 0.5, plus 0.5 plus 0.3 is going to be 0.8, 0.8 plus 0.3 is 1.1. Therefore, we get a sum equal to 1.1, which means it's not valid. All right, that was really fast. Again, I probably covered too much, but I always want to make sure I touch on as much as I can in our hour together. All right. Again, don't forget your exam is due Friday by 11:59 p.m. We don't have an activity for this unit. For the medical unit that we're finishing up. And then, like I said, we are now starting unit 3, which is the introduction to probability. And I covered homework 11 and 12 content. All right. That was really fast.
Yesterday?
I'm sorry?
Wasn't our exam due yesterday?
It released yesterday.
Oh, whoops. Dang it. Well, I did mine kind of late last night, so I might send you
you're
another.
Right. I'm so sorry. No, you're right. Your exam released Monday and was due yesterday.
Yeah,
I'm sorry.
Yeah. Okay.
That is on me. I'm getting my days all messed up. So yes, your exam is already due.
Yeah.
How did I bring those? I'll have them. Thank you, Kirsten. Yes, it released Monday and it was due yesterday. I'm going to be working on grading those. Now we're focusing on the new unit. Yes, sorry, Luke. That was confusing on my part. Anything else that I misspoke about, everyone? Let me know.
Sweet. Well, I'm gonna get out of here. Thank you.
All right. Have a good one, everyone.